d orbitals are a little weird. Okay, we've seen the shapes of d orbitals. Remember, I showed you where are the shapes of the d orbitals. There's the d's. Here's the d's. The s and the p orbitals are kind of straightforward. The s orbital is a sphere. The p orbital has px, py, pz coming out, or whatever you want to define them. The d's get a little funky, and the f's are like, all right? The thing about the d orbitals is everything holds 2 electrons, right? So it can hold 10 electrons max. Now, when you're filling these, they fill 1 electron at a time. So it's like 1 electron, 1 electron, 1 electron, 1 electron, 1 electron. Once you do that, the next, when you're adding the 6th electron, you go back here and you start to pair them up. So then you have 6 electrons, 7, 8, 9, 10. So the thing about the d orbitals is when you have 5 electrons in here, it's stable, right? You've got 1 in each orbital. Or when you have 10 electrons in there, it's stable as well. So it wants to get to that point. So what they do, these are exceptions. So a half-filled a filled or half-filled d orbital is especially stable. So that means d5 or d10, because the d orbitals hold 10 electrons max, but because there's 5 different orbitals, you put 1 in each one, that's stable as well. Not as stable as d10, but it's stable. So what happens is if you're at d4, what the atom does is it takes an electron from an s orbital and it puts it in the d orbital. Now, why this happens is it makes the atom more stable. How it happens is a little trickier, and they don't fully understand things. This is the thing about science is we just say, oh, stuff happens. We observe things happening, and then we try to figure out why they happen. That's what science is, right? So this is what the atom does, so we try to figure out why it does this. And it does it because it wants to be stable. So if we look at, what do we want to look at? Chromium. Okay. Chromium, if you look at the notation for chromium, it is where's chromium? There's chromium right here. Okay. So that's going to be, we're going to do argon, and then we're at 1, 2, 3, 4s2, 3d, 1, 2, 3, 4. So we have chromium is argon, and then 4s2, 3d4. That's the way we would have written it yesterday. Okay, so if I ask you to do chromium, you're going to write that. But then to get full marks, you have to realize d4. It really wants to be d5 because that fills those 5 orbitals. Okay, see right now we're, sorry, it's going to be going back and forth a lot here. Right now you put an electron in there, 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 and there. If I get an electron in there, it becomes really stable. So the atom goes, well, I'm going to steal one. So it takes 1, and it only ever uses 1. It doesn't take 2. The atom is more unreactive, I guess. It's not the greatest term, but it's happy, right? Like if you look at the noble gases, we're going to talk about valence electrons today. It's a more stable atom. If it's got an electron that's sort of isolated, that can react with things, right? So if it can kind of fill all its orbitals, it's like stable and happy. It won't react. Less likely to react or decay. So what it does is one of these electrons moves into that orbital. So what the actual electron configuration is 4s1, 3d5. And I guess I should put the argon in front of it.
And that wouldn't happen if it was like 3D3, for example?
No. This is more stable. It doesn't happen if you have four s2, 3d3. It's not going to steal 2 electrons from there because this is stable, right? So if you steal 2 electrons, and these are going to be lower, these get filled before these. So it'll steal 1 because overall it'll make the atom more stable, but it won't steal 2 because now you've got an empty lower orbital than these ones. So it only ever steals 1. And I don't like saying steal, it borrows. Okay? Yes. Yes. So when you see D4 and well, you'll see in the next one, it's D9, it'll borrow an electron to make a nice happy shell. So if we look at copper here, copper is argon again, and then it's 4s2, 3d9. The atom goes, hey, if I take one of those electrons from the s orbital, I can fill my d orbitals, and I'm more stable. So then it goes, okay, so it actually is argon 4s1, 3d10. And that's what it looks like. It's not a totally well understood phenomenon, but we know it happens. Okay? So when you see something ending in D9 or D4, be aware that you've got to borrow an electron and move it up into that orbital. Okay? Is that okay? It's what? It's communism. It's for the greater good. Socialism. I didn't know it existed. Okay. Is that okay? All right. Next page, peoples. Now, what if you have ions? What's an ion? It's a charged atom. So that means you've either lost electrons or you've gained electrons. So this changes the electron configurations. So electrons get removed or added to the outermost orbitals. Okay. So the orbitals that are further away from the nucleus, the electrons get added into or taken away from. So we're going to look at anions. Anions are a negative charge. If you're negatively charged, you've added electrons. Okay? So phosphorus 3 negative. So regular phosphorus in core notation is neon, and then it's 3s2, 3p3. That's straight up elemental phosphorus. We have phosphorus -3 charge. So how many electrons have I added into it? You've added 3 extra electrons, right? That means 3 extra electrons. Yeah. So how many electrons can the p orbital hold? It can hold 6. So they go into the p orbital. So this actually, so phosphorus 3 negative is equal to neon 3s2, and then those electrons go into the p orbital, and you get 3p6. Okay? Does that make sense? You just dump them into the empty orbital. It has to, because it can't. Because if you look at this, the next orbital is going to be 4s2, which is going to be a higher energy level. Like you're going to go flip down to the bottom. That would be the next available one, right? So there's still room in the p's because there's 3. So there's 3 p orbitals. Remember they look like this? Like that. And there's one that comes out of the board like that. So this one has an electron, this one has an electron, this one has an electron. That's regular phosphorus. There's still room for 3 more. So we just dump them in here. Okay? This is how you represent electrons. But I'm not going to ask you that. Okay? It would go into the 4s2. The next one down. But it would probably, that would take a lot of energy most likely. It wouldn't be super happy because, no, but they would just dump in. You just start filling, right? It's just like creating not a new atom, but a new, you just start filling orbitals from lowest to highest. The reason it would stop at P3 is if you look at your periodic table, here's phosphorus. If you add 3 electrons, 1, 2, 3, why would it stop there? It's a noble gas, and everybody's happy as their noble gas, right? That's what everything wants to be, is a noble gas. And the reason it's happy is because all of its orbitals are filled. All right. Okay. Now, cations. Cations are positively charged. If you're positively charged, that means you've taken away electrons. So, when you're removing electrons, there's an order that you have to follow. PSD. They use people should dream, or you can just remember PSD. Okay? All right? The reason this is the order is because the p orbitals are further away from the nucleus. The nucleus is full of protons, which attracts the electrons. So if you're, this is going to be quite a demo. If the cookie is the nucleus, the jar, and you're standing right here, really close to it, it's pulling me in. That's an s orbital. The p orbital is like way over here. There's less of an attraction. It's really just a function of distance. Okay? And I'm going to show you a simulation here in a sec, or sometime today, that sort of illustrates the size of these things. So it pulls the electrons from the orbitals that are further away. Sorry? We're not going to do this. It depends on where it is, what the distance from the orbital. So if it was S, so if you're talking about the lanthanides and the actinides that get fit in there, it'd be S, so it'd be P, S. I have to think about that, actually. All right, tin. So the regular form of tin is, what's the regular form of tin? Is going to be krypton. Is going to be 5s2, 4d10, 5p2. So you can see it's the primary quantum number, so it's probably going to be last, right? Like the 5 in front is the primary quantum number. That's why it's PSD. Okay? Okay. So, tin 2, how many electrons have we removed? Nope, because we're positively charged. If you're positively charged, you've taken electrons away, because electrons are negatively charged.
Yeah, that's fine.
Okay. So, where am I moving the 2 electrons from? What orbital? Yeah, the 5p2, right? So, tin 2 has a electron configuration of krypton, 5s2, 4d10. These ones are gone. So there's nothing in the p orbitals. If we go to tin 4, I'm removing 2 more electrons. Where are those ones coming from? the s orbitals, the s. Look at this number here, 5, 4, 5. That tells you sort of the energy level of these things. So you literally just, the bigger that number, and P is always before S. So then the next two come from the 5S. So tin 4 is just 4d10. Okay? And again, you can see why it wants to remove from the S, because the d orbital is filled. It's stable. Okay? Vanadium. Vanadium by itself is argon, 4s2, 3d3. But it's 2 plus. So where are those 2 electrons coming from? It's going to come from the 4s2, right? So those go away. And so the actual electron configuration is argon 3d3. It is, but remember d orbitals. Well, if you look at this one, d orbitals want to be filled, so that's why that one is stable. And this number here is indicating sort of the energy level. So you go from the higher energy levels first. So the 5s and the 5p have sort of the same energy level. The s is going to be closer, the p will be further away. The d orbitals are bigger, but they have remember, it's like probability. Electron density is close to the nucleus.
So, like, if you're removing the
P's always get pulled first. Okay? Because I'll pull up the simulation in a sec here and show you, see if that helps, okay?
So, for the D, you never remove it?
You do. If I said vanadium, this wouldn't happen, but if I said vanadium, oh my gosh, come on.
What that is that?
Why don't you want to write?
Is it going to be an old-fashioned board method?
There we go. If I said vanadium plus 3, say, right? You would take the 2 electrons from here, but you got to take one more. So then you would pull it from there. So then you would be, this would be unstable, but that's okay for the purposes of this demo. Then it'd be 3d2.
So, it is like the last.
Yeah, it's the last one to get pulled. Okay? All right, so when you form ions, why is it tin 2, tin 4, vanadium 2? What do they want to mimic on the periodic table? Like O2 minus. Everything wants to be a noble gas. They want to mimic noble gases, right? Because then they have nice filled orbitals. So they're said to be happy. Configurations to noble gases are said to be, so this is the word, you're isoelectric, electronic. If your electron configuration is the same as that of some other atom, you're isoelectronic. All right? Yes. You can go watch it if you want. Okay, I'd like you to do those ones, please. And I'll put the answer key up in a sec. What are valence electrons? Yes, the electrons in the outer shells. All right. they are not in the core. Okay. So, and they also are not in filled D or F orbitals. So if it's a filled D or F orbital, they are not considered valence electrons. All right, because those are stable. So they're the ones that take part in reactions. So if we have aluminum, the core notation for aluminum is neon 3s2 3p1. How many valence electrons does this have? Not one. It's anything not in the core or in a filled D or F orbital. The core is this, the noble gas. So this has 3 valence electrons. 2 in the s orbital, 1 in the p orbital. 3 valence electrons. Let's just write a table here. Valence electrons. Okay. What's the core notation for gallium? What's the nearest noble gas? Argon. And then it's going to be what? Four S2, 3D10, 4P1. How many valence electrons? 3. Anything not in the core or in a filled D or F orbital. The D orbital is filled, right? It's stable. It doesn't want to take anything away. So the S2 and the P1, so it's got 3 valence electrons. What about lead? Actually, you do the electron configuration of lead. Sorry?
We can do it. I got it right here.
Okay, just hang tight. Let them get there. How many? So the configuration is 6s2, 4f14, 5d10, 6p2. So the only ones that we worry about are those ones. All right, the P and the S. So this has got 4. Okay. All right, you do the last 3, please.
Do a little transfer on the last one.
Sorry?
Do a transfer on the last one.
I haven't even done the last one yet. Or what do you mean a transfer?
49.
For S2? Oh, it's silver. Ooh. Oh, I have different ones. Okay, now I have to do them.
Maybe you have to do them.
Well, it's different than my key here. I actually have to do some work. Oh. Whoops. freeze this.
So silver would only have one valence electron, and that makes sense because ionic charge is flexible.
Manganese. That's not a good question.
What is? What?
I'm just talking to myself. Go. Boom. So noble, it's a noble gas, so it's got 0 valence electrons. Manganese is probably not the best one to put on here, but I guess if we go by the strict definition, it has 7 valence electrons because it's not a filled d orbital. Now, I just looked it up because manganese isn't great. You can't, I just said earlier that a half-filled d orbital with 5 electrons is super stable, right? You can use those. It's not common. The 2 common valencies of manganese are 2, which makes sense, right? Because you've got the 2 electrons in the s orbital to react, and 4. But it can have valences from 1 all the way up to 7. All right? So it does have valence, but the common one is 2 and 4. You can use these. It just doesn't really like to use them. Okay? That's the thing about this stuff. There's always exceptions. So that's not the best example, but by our strict definition, it's got 7 valence electrons.
So this is just like
The outermost electrons.
So what do you mean when it can have like 2, like the most common ones?
Well, like manganese, the most common valencies, like charge on it, is manganese 2 and 4. And the 2 makes sense like that. Sorry, when I say valence, it means the charge. Yeah. Okay. The silver is a good question, though. Okay. So silver, if you write it out, you get this. 5s, krypton 5s2 4d9, right? But does it want to be d9? No, because it's 1 electron away from being stable. So what it does is it steals the 1 electron from the s orbital. So you get 5s1 4d10. So then this is the stable atom. So when you look at it, how many how many valence electrons does it have? 1. What's the charge on silver? 1 plus 1. So it makes sense. Okay. The manganese isn't great because there's too many exceptions. All right. But this is a good question. Like that would be good for a test or a quiz or something. Okay. All right. Let's just talk about trends in the periodic table.
Yeah, did you start recording again?
Yeah. All right. Okay. Next bit, but we're just going to look at some stuff here. Where's... There we go. Okay. If we look at this, this is an electron simulation orbit. Electron, like putting electrons into the orbitals. If we start with hydrogen, there's hydrogen, right? I put 1 little electron sitting in the center, 1s. Okay, we would say spin up, spin down, plus 1/2, minus 1/2. Remember the spins are positive 1/2, negative 1/2. I'm not going to ask you that, but that's what they are. As soon as you go to helium, we're putting another electron. It goes into this orbital. Why did the center get bigger? So you watch. Watch the center. Why'd the center get bigger? What determines an atom? Proton. You're putting another proton into the nucleus, right? So the nucleus is going to get bigger. Okay. So then, and we got 1s2. There's the configuration right there. We go to lithium. Boom. Look how much bigger it got. Why did it get so much bigger? Because now we have a new orbital, 2s, right? So it gets a lot bigger. Go to beryllium. I plunk another electron into the orbital. All right, so I got 1s2, 2s2. If I go to boron, now what orbital am I going to plunk an atom in or an electron into? It's going to be a p orbital, right? And I got that thing, right? And then you start to fill those. So then it's px. There's the py for lack of a better term. Pz. So now things are getting weird, right? Still got the nucleus right at the center. What happens now when I put one more electron and I go to oxygen? Where does the electron go? It's going to start to pair up in the p orbitals, right? So oxygen, fluorine, neon. Neon's the happy one because it's a noble gas. Everything is paired. Go to the next one. What's going to happen when I go to sodium? I'm putting another s orbital in there, right? Boom. So it gets bigger. Okay. Now we're way out here. And all the p stuff is in here. And then you start filling it. Boom. 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 What's happening to the size of the atom? Watch when I go across. Where was I? We're here. Here, I'll mark it on the board. This is the outer shell. I shouldn't say shell because that's Bohr model. This is the outer orbital. Okay? Watch that bit when I start going across. See if this works. What's happening to it? Even though I'm putting p orbitals in here, what's happening to the size of the atom? It's shrinking. As you go across a periodic table, the size of the atom shrinks. Why? Yeah, that's another way of saying getting smaller, though. But why is it getting smaller? More what? Why is the attractive forces getting stronger?
There's more magnetism. More electrons.
There's more electrons. You're putting more electrons in here, but why is it getting smaller?
Because the protons.
You're putting more protons in as well, right? As you go, what is this number? This is the proton number, right? We're adding more protons. So the charge in the nucleus is getting stronger and stronger, and it's pulling the atom in. So it's almost counterintuitive. As you're filling up the orbitals, the atom actually starts to shrink. So as you go across a periodic table, the atom gets smaller. As you go down the periodic table, the atom gets bigger. Like if you go all the way to argon, there we are there. So it shrunk whatever this much is, a bunch. Okay? Now, we're at argon. So if I go to the next one, all right? So I'm going to go to potassium. As soon as I go there, what is happening? I'm at 3p, 3s, 3p. What's the next one? 4s, right? 4s. That's a new orbital. Orbitals increase. When you jump to a new quantum level, essentially, that's when the atom gets bigger. So as soon as you go to potassium, boom, now we're way back out here. And then what's going to happen as we go across? Well, I should mark it, shouldn't I? because then it's easy to see. So we're here. And I go calcium, scandium, titanium, vanadium, chromium, manganese. What? I'll zoom out in a sec. But I care just about this bit. All right? That's the outermost of the thing. And you can see why the S, oh, it doesn't matter. Manganese, iron, cobalt, nickel, blah, blah. Some get bigger, some get smaller. But in general, as you go across, it tightens up. Okay? So, let's go back here. We got like 10 minutes left. We'll just fill this out and then we'll talk a little bit more about it tomorrow. When going down a group, the properties of the element are affected by the increasing size of the atoms and increasing distance between the nuclei and the atoms and their valence electrons, i.e., atoms get large going down. I'll say big because adding you're adding orbitals. When you go across the period, you start to shrink the size of the atom, but because the nuclear charge is getting bigger. Okay, so as you're going across, the different number of valence electrons and the nuclear charge, which is the number of protons, determines how things react. So atoms decrease in size left to right. Let's just stop there today. I feel like I've talked enough.